Tu projettes?
Ouais.
T'as les slides alors?
Quoi?
T'as les slides.
Comment ça? Ouais, le réseau a fonctionné. Attends. Tu veux les faire?
Non, j'en suis chaud.
Non,
On dirait que tu les as devant toi.
Hein?
Tu les as devant toi.
Et toi? Good afternoon, everyone. This is the Spring Working Group meeting. Please be seated. We are ready to start. And please close the doors behind you. The note well. You've seen that in each and every session you've attended so far. I won't go through that, but please make sure you are aware of its considerations. Minutes. Who is volunteering to take minutes for us? I see Patrice raising his hand. No? No, that would be a help. If nobody volunteers, then so be it. If someone wants, please go on the Etherpad and we'll take minutes ourselves. So, working group status. Thank you. So back in Seoul, that was a slide with blinking red on it. We had missing IPR answers. We had a lot of delay. And we had set quite an aggressive target, and we've managed to reach it. So thank you to the working group. Thank you to the reviewers who made comments during the last call. Thank you to the authors who have responded quickly this time and addressed the comments. And thank you to the shepherds, specifically Stéphane, because the others were Bruno and I. So thank you very much to everyone for having made this reality. And what's the reality is that we have submitted 7 documents to IESG. So of course you always have to blame someone. So it will be me, because it should have been 8 rather than 7. We're missing the LDP interop document, which was planned as part of that package, but it should be sent to IESG soon. And you should read Adrian's draft on the definition of soon. It's only the beginning. Why? Because authors, and this concerns you, please be aware of the different reviews that will be returned to you from IESG or from different directorates. The last call comments, IETF last call, but also all the RFC editor phase and so on, so that we move smoothly. And don't forget to thank Alvaro, who's getting a load on his shoulder to treat these documents. So with that, the working group nearly doesn't have any working group document, only very few of them. We've listed 2 which are ready for last call. we believe, and the authors too. So any cast segments and SR Young. There's a third one, which is not mentioned on the slide, which is the SR conflict resolution. We'll soon be taking a decision on that document, but we expect it to be ready in its current shape to go to last call.
So regarding that last one, SR conflict, I've been involved in the discussion, so I will recuse myself from making the consensus call when it will happen.
So I will do it. Next steps. So since we are approaching the end of our milestones, we have and we will have sent all of our working group documents to ESG. So it is time to start thinking about the next steps. We are opening the discussion today. We plan on continuing it on the list, but we would welcome to see it happening today already on the mic. So it's really open. Should we recharter? Should we close? Should we sleep for a while? There is candidate new work that we have identified. It was easy because it's already published documents, individual IDs, but you might have ideas that you'd like to share and have discussed with the others. So the floor is yours to have your opinion on our future. The first one that speaks triggers the discussion, so thank you.
Stefan Nikowski from Orange. My point of view is that we have now multiple implementations of segment routing, but there is very few deployments. It's just starting, so we don't have a real operational feedback on how it works on a live network. So there may be some things to change in the future. So clearly closing the working group now may be too early.
Anyone else wanting to propose funky ideas? Yes. Thank you, Stefano.
Hi, Stefano. Yeah, I agree with Stefan. Closing the working group is probably the most nonsense idea at this stage. Maybe we should wait for the next presentations about segment routing policies and the network programming and see if those two drafts fits into the current charter or if they require rechartering or extending the charter of the group. But clearly there is still quite a few things to do in spring, so for me it has to be addressed.
Hi, Alvaro Rotana, Routing ID. So I agree, closing the working group at this point is something we shouldn't do. I think the two options are recharter or go to sleep. Remember that this working group was chartered originally mostly to do the use cases and the architecture, but all the extensions are being done somewhere else, right? OSPF and everywhere else. So at minimum, if there's nothing else, we need to stay open until at least all those extensions get published. It may be that that is short term, it may be longer term. If there is other work that we need to do, we of course need to recharter. So if we're going to go forward, yes, there's going to be some type of rechartering. But yeah, the decision is not, or shouldn't be, too close, at least not today, because we need to remain open until everything is published.
Yeah, please go on. You're waiting for my permission?
Yeah, yes, please, sir. So while we pretty much done with MPLS v6, it's yet to come, all the possible issues, implementation feedback. We haven't even started in most cases, so again, to kind of reiterate what's been said, closing is definitely too early, and V6 feedback should come into the group and result in more work and fine-tuning.
AC Lyndon. Even without rechartering, there's a few documents that are proposed, even working group documents, for instance, the spring conflict resolution that we took into this working group because it was generic across all the protocols and entities assigning labels. So, that would need to be done. And there are additional, I would call them use case documents as well proposed. So even before we recharted, there's plenty of work during the recharting process. And we actually took all those details out of this extensions like ISIS and all the details of conflict resolution out of the IS and OSPF drafts and centralized them in the conflict resolution. So I think that's a really key document, right?
No, yeah, I agree, and I've mentioned it, AC. It is part of the documents that need to be processed by the working group before that's taken for granted, before we start deciding on that.
Hi, this is Uma Chanduri. So definitely not closing. I also wanted to indicate that what Alvaro said, the work that is being done in protocol working groups, any of the draft which is going to working group last call, it's better to put it here so that people can see the gaps and, if anything is missing or anything is not fitting into the architecture, I think people can have a chance to look into this in this forum.
That's the problem of not having a minute taker. We do it ourselves. We have a lag of responsiveness. You're taking? Oh, that's lovely. And that's the agenda. So we'll be discussing, Stefan will come on the mic on non-protected path. We'll have SRT from Stefan as well. SRv6 network programming from Kamran, and the last one on separating routing plane using SR from Shraddha. Stefan, you're up. C'est quoi ta draft? Non-protected path?
C'est le premier, c'est dans l'apparation de l'autre.
Okay, so the first presentation is about how do we build non-protected path using segment routing. So in Seoul, we presented the first version with a couple of scenarios, couple of theoretical possibilities to build this non-protected path. And the goal of this draft is really to find a single standard solution. So all implementation will implement it. So we will ensure the deployability of this kind of use case. So globally, we identified 5 different possibilities to build this non-protected path. So the first one is to use only adjacency seed that are not protected. So the adjacency seeds that are advertised with the B flag unset. The second scenario, from a theoretical point of view, was to use adjacency seed combined with strict SPF node seed. The third scenario is to use still adjacency seed combined with node seed, where we are adding a special new flag to tell that this seed must be protected or not. Fourth scenario is still to combine adjacency seed with a node seed, but we are managing the protection of the seed by a purely local policy on each node. And the final scenario is to combine the adjacency seed with some binding seed. So we tried in the draft to do an analysis of all the different scenarios. So this is a kind of summary, but there is more details in the draft. So we are analyzing the impact on the label stack size. So for example, the adjacency seed only solution has a huge impact in terms of size of the label stack. This must be taken into account as the hardware today may be limited. That's why combining with whatever binding seed and node seed provides something which is better. Now, in terms of control plane states that we have to maintain, so if we need to advertise a couple of more adjacency seed, it's not really a big deal. While adding node seed is more impacting because it's global, so each node will have to install it. So there is an impact on the control plane, but also in the data plane. And for the binding seed, it's more variable. It will really depend on the intelligence of the controller, how it will be able to share the binding seed between all the paths that we will provision in the network and so on. So it's a bit hard to evaluate, but yes, there is something in addition. How much it will be really implementation dependent. We are also looking at what could be the impact on the convergence time of a network, because if I'm adding new things in the forwarding table globally to converge all the forwarding table entries, it will be slower. So in this case, the adjacency seed and the binding seed scenario is clearly better. In terms of what is the impact on the computation of the path? So if we are using adjacency seed only, we just need to look at the flag and select the right adjacency seed. So just look at the B flags unset and we can select it. For the strict SPF and adjacency seed, it's also a similar kind of policy. We can select it easily. Where it's more complex, it's using nodal segment with a local policy. We need the controller or the computation engine to be aware about what is the policy configured on each node. So this clearly brings a higher level of complexity. And for the binding seed, if we want to try to reduce the number of states that we are introducing in the network, we need a kind of smart controllers that will be able to place the binding seed in the network to bring the ability of sharing those binding seeds for multiple paths. In terms of protocol extension, the only scenario that requires a new protocol extension is the node seed with an additional flag. Otherwise, we already have the existing mechanism to do the job. There was one point raised in the discussion, is that for those non-protected paths, do we allow ECMP or not? Clearly, it's a question of use case. Sometimes it may be allowed, sometimes not. For example, in our use case, we want also to avoid any kind of rerouting. So even ECMP, we want to avoid it. So in this case, only the adjacency seed and binding seed is authorized. So globally, if we are look at all the requirements, only the adjacency seed and the binding seed scenario is providing a full coverage of the requirement. Now, depending on the use case, if you want to relax some of the constraints, so telling that you authorize some transient rerouting, yes, you can use nodal segment scenarios. One other point that is interesting to look at is that for the binding seed scenario, depending on the protocols that we will use to program those binding seed, we may need to already have a protocol session to all the nodes of the network. Let's take the example of PCEP. For example, PCEP, it's a client-server protocol. So I need to have all my PCCs to be already connected to the controller to be able to program the seed. So this may have an impact, for example, on the controller because we don't know where we want to program a particular binding seed. So the better scenario will be for the controller to be able to dynamically instantiate a protocol session, for example, when it is needed. It's possible, for example, using BGP. If we want to do it using PCEP, we may have to change some things in the protocol. So the conclusion of our analysis, but please let us know if you agree or not, is that the best approach is clearly to use only adjacency seed with B flags unset. It's the easiest one, but there is a huge impact on the label stack. So clearly, if we look at maybe in 10 years, yes, that will be cool because we will have the hardware to do so. But in the meantime, we really think that the transient solution may be to combine it with binding seed. So this is the global idea that we want to push. So yes, we need to have your feedback if you agree or not, because we really want to push the vendors to support, to have all the vendors supporting this behavior to enable this use case. So yes, do you agree with this proposal? Do you have any other comment? And we would like to put this document as a working group document. So yeah, feel free to give your feedback. Julian?
Julien Meric, PCE co-chair. Just a side comment. I fully support this kind of initiative because it pretty clearly tries to address interoperability issue that we may face in deployment. So full support. Just side comment on the PCEP thing you said before. There is no change required in the protocol to set up a session in the other direction. Good. It's just a matter of identifying your ping addresses. So
what?
Your addresses to initiate the connection.
Okay.
So you may get from the IGP, GPLS, whatever. So there is no such a big gap to go into PCEP for that. I'm not saying it's a good thing. Just
thank you for the information.
No such a delta. Thanks.
Justin here. So support there's valid use case and needs to be done. With regards to PC, and it's John here, when we talk about seed expansion through binding seed, we need to establish PCEP session on demand. And so there's BGP auto discovery for PC. We need to converge how we do it and security consideration. Because it's same case in BGP. Today, you need to explicitly configure session to open socket in kernel, right? So we need to figure out how to do it so security isn't compromised. But it's needed.
Yeah. For BGP, as far as I know, in terms of implementation, some implementation are already supporting the fact of authorizing a set of peers, for example, a range. So if your PC address, if your controller address is within the range, you will be authorized to dynamically instantiate the session without doing additional configuration on the peer. Any other comment?
Alberto than Cisco. I'm okay. Don't worry. Yeah, it's time. Speaking as a working group member, so is the plan for the draft to say what? This is a mandatory to implement option, or to suggest that that option, first option that you mentioned, is the or what?
Yeah, the goal of the draft is to really to say, if you want to implement this use case, you have to do it this way, and you have to implement it this way. So using adjacency seed only or using binding seed, and that's all.
So if you want to implement this, so it's not a mandatory to implement part of the Spring.
Yes.
And
so
you think this should be a standard document?
That's a question. As we do not have any protocol extension, yeah, I don't know.
Okay.
I don't know.
Just think about it.
Next one. Next presentation.
I'd like a show of hands on who has read the document, please. Okay, something like 10 people, 10, 15 people. Thank you. Guys. c'est quoi? C'est ça?
Yes, it should be this one. Okay, so next presentation is about segment routing, traffic engineering policy. So the goal of this draft is to give some details on how must be implemented the segment routing traffic engineering, and it's mainly focusing on this concept of segment routing policy. So we define what is the policy, how does it work, what are the components of this policy, and what are the different methods that we could use to steer the traffic into this its policy. So it's completely data plane agnostic, so we can use SRv6 or SRMPLS. We don't really care. It's very, very generic and agnostic to the data plane. So the draft is starting with some generic consideration about traffic engineering, but it's very similar to what is existing with RSVPT today. So this SRT architecture is for sure multi-domain capable. So we are able to learn topologies through also multiple ways. We can use BGP-LS, IGP, netconf, or whatever. It could be single area, multiple domain. Yeah, it's clearly straightforward. The main point of this draft is this concept of segment routing policy. It's identified, the key of this segment routing policy is a tuple, which is identified by the headend, where this particular policy will be instantiated. There is also the endpoint, so what is the target of the traffic? What is the endpoint for the destination of a traffic? And we have also a notion of color. This notion of color will help some specific traffic steering. So we may be able to identify some destination, tag them with a specific color, and automatically those destinations will be steered towards the policy. So this policy may be also created in multiple ways. It could be instantiated through BGP, PSEP, netconf, or CLI, or any kind of interface. This SR policy, so it's detailed here. So we have this key of head, color, and endpoint. And within this policy, I may have multiple paths. It could be multiple paths coming from the same source, so for example, the same protocol, or it could be coming from different sources, so one policy coming from one path coming from BGP, one other path coming from PSEP, really depending on how we are implementing it. So we have a preference among the paths. So only the path with the best preference will be for sure installed in the forwarding table. And within the path, we will have the seed list, so the list of seed to push onto the packet. And in case we want to use multiple paths, we have the ability to have multiple list of seeds with a different weight if we want to do an equal cost path load balancing. So this notion of segment routing policy is also linked to the binding seed. So the idea is for each policy, we associate automatically a binding seed. So this clearly will help the traffic steering. We will see what would be the traffic steering methodologies just the slide after. And globally, it will, as I shown in the previous presentation, using a binding seed will always allow to reduce the label stack that we will push into the packet. So this is one of the focus goals of the binding seed, so reducing the size of the stack, but we are also hiding some part of the network. So let's, for example, here we have a core network with a first data center and another one. If, for example, for a particular path, we are on the DCI node instantiating a binding seed for each data center, it will allow to completely hide what is happening, for example, in the core network. So it will hide the churn, it will hide the complexity, the engineering of the network, and so on. So how can we steer the traffic? So the first method is the source will of the traffic will directly put the path, so the seed list using a particular, for example, here a binding seed. So, for example, to steer the traffic to Z, it will use the adjacency segment from A to B, an adjacency segment from B to H, and then H will expand the binding seed that he advertised, and it will expand it to adjacency seed from C to D and D to Z, and finally we will reach C. So this is the first way to use the segment routing policy. So the source is directly putting the corresponding binding seed. We are also able to use this segment routing policy with BGP routes. So here we can use this notion of color. So for example, we are here receiving a BGP route coming from Z, so next up is Z, and we are associating this color of C. So we will configure a kind of policy, so inbound BGP policy here to tell that if you match the color C, then you are allowed to look at some traffic engineering steering policy. So automatically it will look at the segment routing policy which has a color C. So it will, from a forwarding point of view, it will do a recursion, for example, on the binding seed. So my prefix 10/8, I will first push the label L, which was bound to the BGP route, and then I will have an indirection towards the binding seed. And this binding seed will be bound to the list of seed. So it's clearly a hierarchical fib scenario that we are implementing in the routers. So it's similar to what we can do in package and so on. So the idea is clearly to tell that if the path within the policy is changing, we are not affecting the BGP route. Like we are doing today with RSVP, we can also do some class-based traffic steering. So I can configure on particular interface a traffic steering policy to tell that a particular forwarding class, for example, my forwarding class 0 must be bound to the IGP path. My forwarding class 1 must be bound to a particular segment routing policy. So in this case, it will there will be a recursion towards the binding seed associated to this to this forwarding class. So this is the first version of the document. It's I think it's something like 35 pages to read, but we clearly encourage you to read it, and we are welcoming comments, and we will clearly update the document based on your feedback. Jeff?
So the major comment here, the configuration is still very imperative. You're pretty much doing CLI, right?
Sorry?
You're saying if seed value X, do Y. There's some recursion possible, but it's still CLI-driven way. So my proposal for the future specifically would be rather to decouple seed value from what it means. You're overloading it because you're saying this value means that. Rather, we should be able to ask someone else, what does this value really mean? To provide.
Do you mean the value of a binding seed?
Of seed, yes.
Yeah.
So you don't need to go and say, if it's 5, do this. If it's 10, do that. You should be able to ask, if it's 5, what should I do with it?
But the allocation of a binding seed could be done by anyone. It could be dynamically instantiated by the local node, but it can also be chosen from the SRLB by the controller.
Sure. What I mean that the context of value shouldn't be local to the node. It should be closer to business logic than to forwarding.
Okay. AC?
AC Lindum. First of all, I read the document, and it's only a little over 20 pages. It's the same document.
Maybe.
Yes, okay, you said 45, and I thought, man, did I read the wrong document? Okay.
35, no, 35.
Oh, 25, okay, yeah, that's closer if you include all the BS at the end. Yeah, but I'd like to say that I think this document really puts the SRTE and IDR into perspective
Yeah.
And it's a good companion, and that we really need to have a discussion on the IDR list of making that a working group document. Because I think prior to this document, you really couldn't understand and appreciate how one would use it.
Right.
And this puts it all in the right perspective.
Right.
Yeah, in answering to what AC just raised, indeed, before that document, we had the BGP SRT policy. We removed from the IDR draft whatever is related to the definition of an SR policy. And we left in the IDR, in the BGP draft, only the signaling, the control plane part, which is just the BGP mechanics, in fact. And the point that Jeff raised about CLI and how to impose a given value for a binding seed. In fact, we already have this mechanism because we have a BGP-LS draft that allows you to advertise an SR policy. And what we would need is a very simple extension to that draft, so to use the same NLRI, so to request a given binding seed, not only to signal what you have provisioned, but also you signal your requirement and you receive back with BGP-LS the binding seed corresponding to the policy that you have to instantiate. So I think all the containers are there. We just have to redefine the, the LSP distribution draft, add a few bits there.
Thank you.
C'est qui l'a fait? Oui, Cameron. Oh putain. Putain, les gens peuvent pas me faire du...
Give me 1 second. You have it?
Yeah. Hey, hello everyone. I'm Kamran. I'm presenting this version 00 draft SRv6 network programming on behalf of this long list of authors. So SR network programming is basically, refers to capability of an application that allows an application to encode any complex program by means of set of individual functions which are distributed all across SRv6 network. Example of functions could be underlay LSAs or overlays or complex functions implemented within some VM or container. So this draft is basically a key SRv6 document that describes SRv6 network programming concepts, the various functions which are associated with those, and the use cases and use cases which use these functions, those use cases are illustrated at the end of the document. So specifically, the document talks about local state functions, transit behavior for nodes. The control plane is outside the scope of this document, but we touch upon a little bit about the control plane and their role while advertising or signaling these sets. Also, document talks a little bit about counters and security. And at the end, we have some use case illustrations which puts all of them together to better explain these functions. So quick status on SRv6 network programming. So going back to this slide. So this SRv6 network programming has already a larger wider community support. There's lots of vendors and operators which are already on board and working closely. And in future, we expect to have a few more joining as we go further. And in terms of implementation, we already have a few interoperable implementation which have either implemented most of these functions defined in the document, or at least some of them which are already working, and rest is in progress. So we encourage you to look at this page, Open Software Project page, which already lists two implementations. Which one of them is VPP based, Cisco-funded implementation, which has software support for all these SR-v6 network functions, and another one is Linux kernel-based initiative to make it SR-v6 ready. Right. So before we go to the function, so a local set is a set which is an IPv6 address having a specific instruction bound to it. So we assume that we expect that every router has a table of these sets, what we call my set local table. And this table basically captures all the sets which are SR-v6 sets which are explicitly instantiated on that node. In other words, the node which is n is a node which is it's a parent for all these local sets. The function of this table is basically to keep to basically maintain all those local sets instantiated, plus their instructions which are associated with those sets, as well as any parameters that are required to execute the instruction. A local set could be bound, could be routed, but it doesn't have to be routed. Most often, it is routed via shorter prefix length path. So if it is not routed, then typically a set list will have a routed set preceded by, a non-routed set will be preceded by a routed set, so that finally traffic could be steered to a non-routed set. This is no different than local segments in MPLS, where you need to have first a global segment preceded before the local segment. So we also in the document we also present that you can basically divide a set into kind of in two parts. One is the locator parts, another is the function part. Locator part is the one which basically used to route which is used to basically route traffic to the node which owns that set, whereas the function part is really local part and which specifies that local function that is implemented on the node, which is located by the locator field of this set. Now you can divide this locator and function the way you like. There's no assumption or restriction in the draft that we put. You can have /64, /68, /48 for your locator, and rest for your function. So also, if there are cases where a function is an argument, you can even further divide a set, to specify your arguments in the least significant bits out of your function. For example, for the application running a VM case, they may require some arguments. So this is what this framework in the document we have. So about the set functions associated with all these sets in the my set table, there are certain well-known functions that we have already listed in our document. It's a non-exhaustive list, and in future we expect to have more functions added. And also document specifies, for each function on a very high level, a processing algorithm when a packet arrives and what you need to do with the packet when you process for a given set. We will not talk about those algorithms in today's talk, and you are encouraged to look at the draft if you wanted to look at further details. So this table just summarizes this table and the next page table. It summarizes all the local state functions we have defined in the document. So basically, n.x and n.t, these are the functions which are topological functions, typically signaled and advertised by the IGP. And their forwarding behavior is, some of this behavior is already specified in an SRH document draft submitted earlier and already being present. However, their forwarding behavior is a little bit different. For end is the base function, where you basically update the packet. You decrement your SL, update the packet destination, and forward after doing the lookup. Where n.x is like adjacent set function, where you update your destination address and forward using a L3 cross connect adjacency. It can be also L2 adjacent set as is specified in one of the ISIS draft. So first three functions are really core functions to implement our TILFA and SRT policies and advertised by IGP. The next set of functions which this table captures relate to VPN, mostly encapsulation, L2, VPN, L3 VPN. So for example, for n.dt6 function, this is a function that is associated with a local set. And what it is telling us that when you receive a packet, it's expected to be encapsulated through an outer IPv6 header and possibly an segment routing header. So you decap outer IPv6 header as well as SRH header, and then do the further forwarding of the decapsulated packet after doing the lookup. So this is equivalent to IPv6 L3 VPN per that we know in MPLS. Similar version for DT4, which will do the same thing, where L3 VPN v4 will be encapsulated within SRv6 outer IPv6 header or header plus SRH. DX6 versions of these functions are equivalent to cross connect or per CE, as we know in MPLS. But in case of in terms of decap, they share this common functionality. Only the forwarding is where the difference is. In one case is a lookup, other case is cross connect. And finally, there's also L2 VPN decap function that is listed here, where encapsulated packet is L2 frame, and it's encapsulated in SRv6 header or SRv6 header plus SRH. And decap has to happen. So this is really egress P functionality that these functions are defining. The other set of functions, Stefan just went through SR policy draft, and we talked about binding set. So n.b6 is a binding 6 instantiation of SRv6 data plane. And it is used to implement basically SRv6 policy in our draft. If there's a policy which requires us to change source address, so in those cases we define n.b6.incap functionality. And then this n.bm is also a binding set instantiation, but this is to cover the case when we are trying to have a scalable traffic engineering policies which span across multiple domains, and one of the domain is MPLS domain. So if you want to traverse an MPLS domain, still implement end-to-end SR scalable policy, then use n.bm sit function. And finally, there are a couple more functions. In the interest of time, I think skip. But basically, n.as and n.am are functions that are for service chaining, which are done through an SR unaware application. In both cases, important point to note is that these are SR unaware applications, and they do not need to know and cannot look into SRH header. So in one case, outer IPv6 header is removed, and SRH is removed. In other case, the outer IPv6 header has been updated with the actual final destination for the packet, so that this SR unaware application can process just based on the packet header rather than looking into SRH. So one point to highlight that for this topological IGP end functionalities or end set functions that we have specified in the document, there are two variants of these functions that we have specified. And these two variants are really related to popping the SRH that is on the packet. And popping meaning cleaning up the SRH or top SRH. And these, so there are two flavors we have defined: ultimate segment pop and penultimate segment pop. Ultimate segment pop is a flavor, which means that if this set is advertised as USP end functionality, then packet will come all the way up to the ultimate segment, which owns this set, and SRH will be popped at the last segment. Versus penultimate segment popping, SRH will be popped at the penultimate segment if this set is a PSP set advertised. And in the draft, we have kept it open up to implementation, that how they wanted to assign and control this USP or ESP behavior. These variants can be enabled or disabled together, or can be disabled and enabled individually. Right. So also we talked about transit node behavior. So by definition, a transit node is a node which receives a packet, IPv6 or SRv6 packet, whose destination is not one of your local set. So basically, it's really a transit for that traffic. So there are 4 transit behavior we have defined. One is a pure transit behavior. This means this could be a pure IPv6 router. All it does is just look at the IP destination and forwards packet according to the destination. And the next 3 are really transit behavior which somehow impose SRv6 header or encap in SRv6. So t.insert is to implement cases where you wanted to you wanted to change an incoming packet and insert SRv6 header and insert SRv6 header or insert an SR header on incoming SRv6 packet for the cases of, let's say, SRv6 policy. Or let's say if you are doing TILFA and you receive a packet and you are already in FRR mode, then you have to impose more segments. In those cases, t.insert is used. The cases where you cannot use a t.insert, you can still use t.encap, where you can encap the incoming packet within SRv6 header and the SR header. And finally, there's also L2 version of the t.encap use case. So as I said earlier, this control plane is outside the scope of this document. However, we listed a table where we have tried to just summarize and observe that what protocols are used to advertise or signal these SID functions that we have listed in the document. So .x and .t is IGP, and IGP is a base topological signaling protocol for topological SIDs in our draft. BGP and IP for all VPN related SIDs that we have listed. We also expect that on every SRv6 node will advertise its instantiated SIDs via BGP-LS, as well as all its other capability, like can I do insert, and if I can do insert, how many SIDs I can insert, and whatnot. So all these capabilities have to be advertised through BGP-LS because BGP-LS is our basic service discovery protocol in this whole framework. Counter, for the counting reasons, counters are also listed in the document so that you can count on local SID traffic, matching and non-matching, processed, not processed, as well as traffic that is steered on a given SRv6 policy. The counters are also there. And for the security reasons, for the security cases, to basically make sure that within a domain of trust, while we are providing SRv6 based services, internal traffic can still use those services. However, we wanted external traffic not to be able to access those. So there are four security rules that or notions that we have, mechanism we have specified in the document that you can take a look. So finally, at the very end of the document, after all this, putting all this together, we have a use cases illustration using an example, which uses almost all the functions that we have defined earlier, how they will be used, what will be the behavior, how insertion will be done, how decap is expected to be done, and how binding set is to be used. So all these use cases are at the end of the document. Please take a look and provide us feedback. So in terms of next step, we're looking for working group input and feedback, and we're looking for any comments and suggestions. Thank you. Any questions?
Who has read the document? Okay, and that's about 20, more than 20 people. Thank you. Thank you, Cameron.
I don't know. Yeah. Yeah, but attends. We have someone on the line. No.
Hello, can you hear us?
Yeah.
Okay, cool. So this is Prem and Milad from Barefoot Networks. Just a quick comment on implementation. So we actually have an implementation of this draft on our silicon using P4. So just wanted to make that quick comment.
Thank you.
Yeah, I think is referring to the previous draft that I presented, that there's already implementation on Barefoot.
Yeah, the previous draft. Sorry, not this one. The previous draft. I didn't see the screen has changed. Sorry. Yeah.
Thanks.
Thank you.
All right.
Give me a second.
Hello, everyone. I'm Shraddha Hegde, presenting the new draft on separating routing planes using segment routing. So the slides are prepared by my co-author, Arkady, and I'm presenting on behalf of him. So basically, the use case here is to support the L3 VPN unicast services. There's an MPLS-based dual plane network. So there are two separate planes. You can see in the diagram, blue and the red planes. And certain traffic has to use the blue routing plane, and it should never cross over to red plane, even if the routing plane is segmented. So if the routing plane is segmented, then the specific traffic must be dropped, and it must not be forwarded onto the other plane. And there is also a requirement where there are normal SPF-based paths. They can use a certain plane, and if the plane is partitioned, they can flow over the other plane. So there are two requirements: certain traffic that has to be restricted to one routing plane, and certain other traffic which can fail over to the other plane. So the requirement is to be able to support fast recovery using TILFA within the plane. So the basic requirements are listed here. So maintain strict routing within the routing planes. So allow traffic to fail over within routing plane, and and do not allow traffic to fail over to other planes, and then achieve ease of configuration and operational management, and also achieve fast reroute on link and node failure. So we have many existing mechanisms which can be used to solve this problem, and we have some shortcomings which won't completely meet all the requirements. We can go through them in the next slides. One is the node admin tags to color each of the planes separately and then use some kind of traffic engineering to achieve this. The second option is to use separate anycast SIDs, one per plane. The third option is multi-topology, empty SIDs. There's also a possibility of using only the adjacency SIDs to build paths through the routing planes, but that has the disadvantage of having a very deep label stack, which most of the software and hardware does not support today. And so probably it's not very practical to deploy using adjacency SIDs alone. So here is a description of how node admin tags can be used to achieve the requirement that we have. So the nodes are colored red and blue according to the plane to which they belong. So PCE, or a central controller, is used to create traffic engineered paths, and then they are downloaded using protocols such as PSEP, to the ingress nodes. So the problem in this with this approach is that when the plane is partitioned, so as long as the plane is not partitioned, it's possible that to keep the traffic in the plane. But once the plane gets its partitioned, like PE3 to PE7 is down, and also PE1 to PE3 is down. So in this case, the traffic will fail over to the blue plane. So, and also the post-convergence path would fail over to the blue plane. So it does not meet the requirement, and it also uses a complex traffic engineering approach. You need a central controller, you need multiple protocols that talk to the ingress node. And so this doesn't fully satisfy the requirements of this use case. So the second option is the Anycast sits. So you could assign an Anycast sit to the all the nodes in the plane, and then you could direct the traffic using those Anycast sits through the routing plane. The problem is very similar to what we described in the node admin tag. So as long as the plane is partitioned, not partitioned, you probably, the traffic remains in the red plane, but when it gets partitioned, the traffic fails over to the other plane, the blue plane. So the requirement here is that the traffic never fails over to the other plane, because there's critical data that is flowing over blue plane, and the requirement is not to mess up the blue routing plane. So the problems are very similar to node admin tag. So third option is multi-topology SID. So multi-topology kind of almost meets all the requirements. And there's also additional benefit that you could do complete separate topology routing by assigning different IGP costs to link to different MTs. But this is MT is perceived to be a very complex operationally, because because of the configurational and operational aspects, and also additional protocol overheads to advertise MT related information. So this draft proposes using new algorithms to achieve the same. So you have the algorithm TLVs in OSPF and ISIS. So the draft proposes 4 new algorithms, which means algorithm 2 to 5, so which means SPF in routing plane. So a new SID called routing plane SID is advertised for each algorithm. So in this, as shown in this diagram, the red planes have the algorithm. They advertise the algorithm 2, and they also have routing plane SIDs assigned to these, which are advertised for these algorithms. So similarly, the blue planes are also assigned with the new algorithm value as well as the new SID. So the segment routing architecture and the drafts provide a very clean separation of using algorithms. So the nodes which advertise the certain algorithm, they are the only nodes that are used for computations for that algorithm. So so here the separate SPF is done for each algorithm, so which corresponds to a particular routing plane. Do you have any questions?
Yes, Greg Mirsky, ZT. So one of the requirements that you set forth includes budget for the recovery, 50 milliseconds.
Yes.
Okay, so is it from when you start this clock, from when you begin this budget, from when you detect the failure?
Yes, this is a normal fast reroute requirement. So
right, but it's fast reroute, it's a local reroute. It's you already have pre-calculated alternative.
Yes, this is exactly similar. There's no difference here.
Right, and usually it's understood it's not for single path. So here you have a control plane involved. So I think that there is no guarantee that you will comply with this requirement.
So the FRR requirements are very similar to the normal IPFRR requirement that we do. So here also you could compute the backup path in advance, and then you program your forwarding plane with the backup path. The only difference here is your backup path also is restricted within the routing plane.
Right, but then you'll need to pre-compute for all possible failures.
It's very similar to IPFRR. So it's like there's a node. So you do pre-computation for all your links that are going out from that node, and also the
I think
nodes.
that if that's because from this seems that you propose the reactive solution, which is recovery. If you propose FRR solution, I think that needs to be explicitly described, because it will have.
I think there is some disconnect here.
It will have different scaling.
Yeah, I think there's a disconnect here, because I'm not proposing anything new for FRR. It's just the same that we use for IPFRR. So the only requirement here is to restrict your backup paths. Your primary paths are restricted to the routing plane. Your backup paths are also restricted to the routing plane.
My understanding, IPFRR is a local computation.
Yes,
you
it's a
are
local computation
talking
here as
about
well.
centralized computation and then distributing it to nodes. So
No, I'm not talking about centralized computation. FRR is still a local computation here. I don't know, maybe you got that. So here what I'm showing here is purely a primary path, and the backup path that I show here, the red path, is computed locally on that node, PE1. So that's not downloaded from the controller. So
it's basically it's computed on the nodes that are impacted by the failure.
Yes, only the primary path gets computed from the.
Yeah, I think that because you put PCE in the picture, it confuses.
Yeah, sorry about that. So the next slide is about multi-level or multi-area support. So here in the picture you have ISI's L2 domain and L1 domain, and then when you have to leak prefixes from L2 into L1, so you could also leak the routing plane SIDs into L1. So all you have to do is to make sure that the algorithm field, when you leak from one level to the other level, you also copy the algorithm field from the SID advertisements. So that would make sure that your red plane remains reachable throughout in each level. So here is a slide on how to do service provisioning. So here the PE7 is assigned with two IP addresses, 10.10.10.7 and 10.10.107. And they have the normal SID, which is shown in black over there, and the red SIDs, routing plane SIDs, which is shown with red. So the services, we have two service prefixes, x.x.x and y.y.y. So x.x.x is supposed to follow the normal SPF path, whereas the y.y.y prefix is supposed to follow the red routing plane. So the service prefix that is supposed to follow the red plane will use the next hop as the IP address 10.10.107. And so when on the ingress, it picks up the SID corresponding to the routing plane. If you see, the packet looks like 100 is the VPN label, and then 16107 is the SID associated with that router PE7, and it uses the SPF path within the plane. So when the plane is, but if you see when there's a single failure in the plane, it still uses the backup path. because there is a path available in the routing plane. But if the plane is partitioned, then the traffic gets dropped, because the red sets do not see any of the paths corresponding to the blue nodes, so they don't program them either for primary or for backup. So next is the BGP DC use case. So this can be further extended to the DCs as well, whereas the DC is also segregated into red and blue plane. And then certain critical traffic is put on blue plane, and certain other traffic which should be restricted to the routing plane is put on the red plane. The way this is achieved is BGP inside the data center, and in the core we have the IGPs. So the routing plane separation within the DC can be done using BGP, wherein you could put policies to, and you could also associate the communities with BGP to restrict the blue messages flowing, blue advertisements flowing through the red plane, and vice versa. And you can see here that so there is a VPN prefix y.y.y which gets advertised with the next hop as PE7, and then there is a BGP prefix SID that gets advertised for this PE7. So this PE7, the BGP prefix SID is used for transport within the data center, and the VPN label is carried unchanged, and on the edge router the next hop changes to PE3 as well as the label changes to 200, and it uses the red IP address as the next hop, and so the path that gets used within the core is the path corresponding to the red plane. This is the SPF path corresponding to the red plane, and similarly in the remote DC, the next hop changes to the edge router PE1. Similarly, the label changes to 300 there. And then again, within this data center, again, the BGP prefix SID is used for transport. So if you really see, so on this edge router, what you see is the VPN label 300 and then the red label corresponding to PE1. And here, when you come here, it gets swapped, the VPN label gets swapped with 200, and then the new red plane SID gets pushed. The similar operation happens at this edge on PE3, where the VPN label gets swapped with 100, and then red plane SID, BGP prefix SID gets pushed. So you have an end-to-end path via red plane, and there's no, this is using all, there's no central controller, or there's no other protocols that are used here. It's just the IGP-SR plus BGP-SR giving you the routing plane separation. So some of the limitations of this solution, there's an additional SID defined, so if you want to call that as a limitation. And the solution is restricted to this use case, we cannot accommodate other TE constraints like link colors or TE metrics and such. So for those, you will have to go back to the central controller based solutions. So here is a comparison of different mechanisms. So the routing plane SID gives prevention of traffic failover to different plane. There's an additional SID defined, but there are no additional protocol overheads or no operational overheads. But the other mechanisms as listed here, the Anycast SID and node admin tag, they cannot prevent the traffic failover to the other plane. They do have additional SID. For Anycast SID, you do advertise additional SID, but for node admin tag, you wouldn't need it. But then there are additional protocol, like you need to deploy a central controller along with BGP SRT or PSEP to be able to get end-to-end solution. So we're looking for feedbacks and inputs on this.
Sure. So, observational comment. It looks suspiciously as complex as multi-topology.
So, so the difference here is you do not have to maintain separate routing tables, or you do not have to advertise multi-topology related information. Also, your configuration, you don't have to do multi-topology related configurations. It's just the new IP address along with the new SID associated with that. So.
Complexity comes from operations, so you're still running SPF per topology, and troubleshooting is
yes,
more
the
complicated.
SPF per topology, that remains common, yes.
Two more comments. So if you continue with it, probably the additional use cases to conflict resolution draft, and you also need to look into mapping server, how you're going to map algorithm between.
I think conflict resolution draft does say that prefix conflicts are within the algorithm and not across the algorithm. So I guess that shouldn't be a problem.
Martin Hornefer, DT. Just a minor remark for the Anycast-based solution. There was the indication PCE would be needed for end-to-end solutions. I would not agree. I'm convinced that it can do as well without any central controller if you just design the network in a suitable way. That's not the main point. What appears to me is that from the use case or application perspective, I see a big overlap between your document and what can or could be done with Stefan's non-protected sits. So I wonder what the exact overlap of use cases is, and if there or what the use cases are which are covered by one solution and not the other. So if the overlap is very big, it might be interesting to actually join the approaches. If it's not, it might be interesting to point out what the exact differences in use cases or applications are. Well, for what appears to me, the main use case I would have in mind would be the same for both documents. So that's why it might be interesting to point out the differences if there are significant enough.
That's a good comment, yeah.
Hi, Stefano. So the good message from your draft that I take is that finally we understand that multi-topology routing doesn't work well. So that's the good news of the day. Now, if the requirement is I don't want to fail over into the other plane, that's only a matter of your strategy in your TI-LFA implementation. There are very easy ways to achieve that without changing the architecture, without extending the protocols. So I think the requirement is simple. The solution is as simple. And here what you propose goes way beyond what we need. So I think that the only part I would agree is on the requirement, but not on the solution.
Yeah, it's possible to say when using TI-LFA, don't create a backup path through the other plane and such, but that would need configuration, and you use policies such as the backup policies that could say do not fail over to the other plane and such, but still that would need a lot of configuration.
Not at all. There are implementations that can do this on the fly. It's just how you identify a plane. That's it.
Tony P. Juniper. Having invented multi-topology, Stefano, you may have to hire better implementers.
Any other comments?
Thank you, Shraddha. Rafi. So I think we're done. Thank you very much. So please do participate on the list to the upcoming discussion on our future, and see you in Prague. Ouais. Allez. La semaine prochaine. On fait ça avant de partir. Ouais, mais j'en fous, ça. On n'a pris aucun action point. Non, mais tu veux, il n'y a pas de point de contention. Moi, je veux bien, hein, mais dans une semaine, moi, je serai plus là. Bien, et toi? J'ai pas de problème. Si tu veux les revoir, moi, je suis pas pressé, mais dis-toi que moi, je te les donne. Je te les donne.